Good afternoon. Today, I'm glad to introduce the next generation silicon carbide MOSFET technology from ROHM. This product is under development by the advanced engineering teams from ROHM, Japan, including Kenji Yamamoto and other team members. I'm from ROHM, US. We are here to support all customers in the Americas region to understand our technology and design with our devices. In today's presentation, let me first introduce the background of silicon carbide technology and market status. Next, we will look at the development target and test results from the prototype sample. We will present data on the static performance, switching waveforms, and dynamic behavior. The improvements in the silicon carbide device will be highlighted. Finally, we will summarize how our new silicon carbide MOSFET can offer superior solutions for power applications. According to market research data, the demand for silicon carbide devices is growing very rapidly in key power markets. Silicon carbide is a wide bandgap semiconductor material. Because of its capability to withstand 10 times higher electric field than silicon, this material is widely considered as the next generation power semiconductor. Silicon carbide power devices have been under extensive research in the past 30 years, and now it is very encouraging to witness these devices delivering performance advantages and becoming commercially successful. In fact, we believe silicon carbide is the key technology today to fundamentally change the design of high-voltage power electronics. Starting from early years of this century, silicon carbide Schottky barrier diodes have been commercially available. The diode products experienced steady growth in power applications. More recently, challenges in the silicon carbide MOSFET fabrication process have been resolved, enabling commercial adoption of the power transistor in a wide range of market segments. Now and in the near future, the excellent reliability and performance of silicon carbide MOSFET will drive up demand in various industries, including the energy sector, electric vehicles, industrial equipment, and the IT infrastructure. With the latest technology and options for high-voltage system design, these applications are becoming more energy efficient, compact, and environmentally friendly, contributing to a more sustainable society. In this trend of silicon carbide-based power electronics, ROHM has been a leader in technology and product development for the past 20 years. In the year 2009, we integrated one of the world's leading silicon carbide substrate suppliers into ROHM Group companies. SiC, based in Nuremberg, Germany, now provides high-quality materials for our silicon carbide device production, as well as for other device manufacturers. After several successful launches of silicon carbide diodes, MOSFETs, and module products, we now offer a diverse portfolio of silicon carbide power semiconductors. ROHM has established 6-inch silicon carbide wafer process to secure the capacity for large volume production. This allows us to fully support the automotive market and industrial customers. This year, we will introduce the 4th generation MOSFET products, which is the latest breakthrough in our silicon carbide technology. ROHM's silicon carbide MOSFET has evolved through a few generations, from the early planar gate design to the unique double trench structure offering industry-leading performance. With design and process advances, from the planar structure to trench, we were able to reduce the MOSFET-specific on-state resistance by 50%. And for the 4th generation, we will further optimize the trench design and bring down the resistance value by another 40%. Normally, when we improve on-state performance of the MOSFET, the saturation current at high voltage will also increase. As a result, a compromise in short circuit withstand time will be expected. This will not be the case for our Gen 4 design. In this device concept, a new cell structure is developed to suppress the short circuit current while on-state resistance is being reduced. This design ensures safe turn-off of the power device during a short circuit event. Now let's look at some test data from the latest samples. as shown in the forward conduction performance chart. With a chip size of 5 by 5 mm, a very low resistance of 12 milliohm is reached, giving it a higher current handling capability than the Gen 3 MOSFET of similar die size. The lower on-state resistance is a result of smaller self-pitch, better MOS interface, and additional process steps to reduce the substrate thickness. With the improvement in on-state resistance, energy efficiency of the power device can be increased, or a smaller chip may be used to reduce the system cost. From the dependence of RDS-on versus gate bias voltage, we can see that the gate voltage required to turn on the Gen 4 MOSFET is lower than the previous product. In Gen 3 device, 18-volt gate drive is needed to bring down the resistance, while for the new generation, 15-volt is enough to fully enhance the channel for on-state conduction, making it compatible with IGBT gate drivers and other power switches. Another important characteristic is the temperature dependence of on-state resistance. Both our Gen 3 and Gen 4 silicon carbide MOSFET will have positive dependence from room temperature to the maximum junction limit, while for the new device, resistance ratio between 175 degrees C and 25 degrees C will be slightly higher. Essentially, this device behaves more like an ideal power MOSFET in theory, due to higher percentage of the resistance coming from the drift layer and less from the MOSFET inversion channel. These silicon carbide MOSFETs can be connected in parallel with good current sharing properties. For a normally off power switch like the MOSFET, a high gate threshold voltage helps keep the device off when 0-volt gate bias is applied during switching operation. ROHM designs our silicon carbide MOSFET with this target in mind. The threshold voltage of Gen 4 MOSFET has a negative temperature dependency, similar to Gen 3 technology, and the target value of threshold voltage is between 3.5 volt and 2.5 volt across the temperature range. With that, we can recommend using 0 volt to turn off the MOSFET without the need to provide negative gate voltages. To further compare the performance between the two generation silicon carbide devices, we performed switching tests using a double pulse setup. The devices are packaged into half-bridge power modules and compared side by side for 600 volt 100 ampere switching condition. External gate resistance is selected to give both devices the same DIDT switching speed. No external freewheeling diodes are used, and the gate drive voltages are the standard recommended values for Gen 3 and Gen 4 devices. This slide shows the waveforms when the low-side MOSFET turns on. DIDT slew rate is set at 5.6 kA per microsecond for both power modules, and we can observe a faster drain voltage fall time for the Gen 4 device. This difference can be explained by a lower Miller capacitance for the new device, which leads to lower turn-on energy losses even though the DIDT speed is not increased. When we look at the high-side waveforms of the same switching process, we will notice a lower recovery current for the 4th generation MOSFET. On the other hand, the rising voltage across the high-side device's drain and source terminals does not trigger a significant increase in its gate voltage for the Gen 4 MOSFET. This behavior is the result of a lower capacitance ratio between CRSS, which is the Miller capacitance, and CISS, the input capacitance. This feature is especially helpful to suppress parasitic device turn-on in fast DVDT conditions. And because of this, faster switching speed can be supported by Gen 4 MOSFET without the risk of shoot-through losses. We can find a similar switching comparison between the two generation devices when the low-side MOSFET turns off. As the Miller capacitance is designed to be lower in Gen 4 MOSFET, faster DVDT helps reduce the turn-off losses. And because the DIDT slew rate remains the same for both Gen 3 and Gen 4 devices, the surge voltage across the drain and source terminals is not increased when we reduce the switching losses. To summarize the switching performance, We found significant reductions in the turn-on and turn-off losses from Gen 3 to Gen 4 devices, compared at the same DI/dt speed. To improve the switching performance even more, it is possible for Gen 4 MOSFET to reach higher DI/dt speed than the limits of Gen 3. The Gen 4 MOSFET has lower internal gate resistance, and it is more capable of high-frequency switching conditions. At the same time, recovery current from the body diode is also much lower for the new generation, especially at high dV/dt slew rates. Overall, we find the switching performance for Gen 4 MOSFET to be superior in every way compared to the existing product. It should fit very well for applications requiring high frequency and high efficiency operation. In addition to the regular switching evaluation, we also compared the two silicon carbide MOSFET in short circuit conditions. With similar chip sizes, the two silicon carbide modules were tested under the same short circuit event at 600 volt bus voltage. To help the understanding of the short circuit waveforms, it is useful to compare the high current, high voltage static behaviors of these two silicon carbide MOSFET. The left side explains how we characterized these two devices to high voltage and current, and the right side compares their behavior in the conduction state and the current saturation state. The solid black line on the right side chart shows the baseline Gen 3 behavior. As the blue curve of Gen 4 reduces conduction resistance on the low voltage side, it would be expected to have higher saturation current if technology remains the same. But because of cell structure optimization in the new double trench design, the saturation current is significantly suppressed to a level comparable to the baseline. With that, the trade-off between on-state losses and the short-circuit capability is substantially improved. The actual short-circuit test waveforms are compared on this slide. Saturation current for Gen 4 MOSFET remains below the level of Gen 3 during the short-circuit event, and it also drops faster when the silicon carbide chip heats up. With similar chip sizes and lower short-circuit energy, we can expect Gen 4 MOSFET to withstand the same or longer duration in short-circuit events. Now we have reviewed the new MOSFET in terms of static performance, switching losses, and short-circuit behavior. We can summarize the key benefits of ROHM's Gen 4 silicon carbide technology. It offers 40% lower on-state resistance at the same chip size, significantly lower switching energy, and no compromises in short-circuit capability. Along with convenient gate drive voltages and minimal risk of parasitic turn-on during high-speed switching, it will be easier to design with and offers performance improvement and cost reduction for power system applications. This concludes today's introduction of ROHM's Gen 4 silicon carbide MOSFET. We would like to thank you for your interest and look forward to working with all customers to design with our new generation silicon carbide technology for more efficient and reliable power conversion systems. Please contact your local ROHM sales office for further discussion and technical support. Thank you.